Hi there everyone, welcome. This is a small demo on simulating a fake quantum computer with Numpy again. This is actually an extension to the previous project or previous uploads. The previous uploads were not having the visualization part where you can't actually draw the circuit or quantum circuit and understand what exactly happening behind the scenes. I was able to include that in this specific module. Initially, I thought of using matplotlib, but matplotlib is a very vast library and it requires a lot of learning efforts I couldn't put on. That's where I thought of using scalable vector graphics or SVGs in short and create those visualizations. One thing I want to tell you here that this is not a true quantum computer. I mean, we are not running this code on a real quantum computer, real physical quantum computer. This is just a mathematical abstraction where we create a fake code using the matrices or Numpy matrices feature and try to understand how quantum computer works. So here is the project, or let's say the module, and the QDirac module is the heart of this project. This actually consists of two lower modules, that is Qcircuit and QDirac. So the Qcircuit is purely built on the SVG and most of the code is self-explanatory, but let me just quickly walk you through the script, or let's say this code. So it has this SVG line and it has an initializer. It has an initializer function and also the draw SVG function, which is basically to draw the circuits, the final quantum circuits, and a wire method, or let's say wire function. And I also have, this also has actually the generic single qubit gate to design, or let's say to pictorially represent the single qubit gate. And it includes the generic multi-qubit gate. Sorry. And a control NOT gate, or this is for the CNOT gate or CX gate or control NOT gate in general. The code is self-explanatory as it is a Pythonic code. So I would advise you to go through the code. And here I have the CZ gate or control Z gate. And of course the swap gate. This is the swap method or swap gate code. And this is the control CNOT gate or Toffoli gate. This function is used to create, or let's say draw the swap gate on the quantum circuit or quantum canvas circuit. And now let me show you the other part. So this is the measurement gate. Yeah, that's it. Moving on to the second module, that is the QDirac 2 code. This is just description about the code. Importing all the essential libraries here. And here I am defining the 2 qubit operation. So one can actually look into this code. These are all helper functions. Mostly, for example, this apply gate is a helper function here, which is basically used to perform certain operations. And 2 qubit gate operation here. And here is the apply CC0 gate method, or let's say the function rather. This is CC0 operation. So this actually forms the CC0 gate, or a logical gate in fact. And here is the quantum circuit. This actually forms the true, or let's say the mathematical abstraction of the qubit. So it has an initialization function and we have a state vector method here. State vector is essentially an n×1 matrix, or let's say column vector, and here is the single qubit operation. And here you can see the single qubit gates are single quantum gates. Quantum gates are unitary operations basically, and these are all Pauli's gates, Pauli's X gate, Pauli's Y gate, and Pauli's Z gate. They are also called, this one is called bit flip gate, and these gates are generally the phase flip gates. They introduce additional phase when you apply it on a qubit. And this is the heart of the quantum computer, that is Hadamard gate or superposition gate. Without superposition gate, it's quite impossible to imagine a quantum computer. And this is a 2-qubit gate again, so this control NOT gate or CX gate, which actually enables interaction between 2 qubits. And here I have the control Z gate. This is another version of CX gate or control NOT gate itself, but this introduces a phase, controlled phase. Also have the CY gate, controlled Y gate, and here is the Toffoli gate, and of course the swap function followed by the measurement in Z basis here, and of course finally the draw method. Alright, so let me show you the Bell state demo here. So Bell state is basically a 2-qubit entangled state where we take 2 qubits and apply certain operations to produce a quantum entangled state or quantum entangled circuit. And I'm using the 2 qubits here. So let's initialize this. I'm again initializing the quantum circuit, and this is the enhanced part of it. Now if I run this, so this is the state post Hadamard gate, exactly here. This is the state. So if you take this 0.0710678 part out of as a factor, so this is essentially 1010 state, which is equivalent of ket plus and ket 0. It's a Kronecker product of ket plus and ket 0. So you see the similarities here. In fact, they are exactly the same. And okay, let me scroll further. Now I'm applying the C0 gate after the Hadamard gate, and this is the circuit. So this is the very entangled Bell state circuit. It produces a quantum entanglement state, and here is the state vector after the C0 gate, and this is the very entangled state or entangled matrix. It's 1 over square root 1001, and we can't have a this state cannot be represented as a Kronecker product of 2 basis vectors. So that's where that's why we call this as an entangled circuit, and this is the overall schematic of the Bell state. Yeah, these are the enhancements I made, and the same has been published in the GitHub. So this one is the final demo, which includes the GHZ circuit or Greenberg, Horne and Zellinger circuit, essentially a multi-qubit entanglement circuit. So in this specific case, I'm using 3 qubits. Of course, we can go for 4 or 5 qubits also. It's feasible with this module. So I'm initializing here, and this is a 8x1 matrix because it's 3 qubits, so 2 to the power of 3, which is 8. So 8x1 matrix or column matrix or a state vector. Now I'm applying the Hadamard operation on the topmost qubit, which is Q_0. I love big endian notation, so but in Qiskit actually this is different. They use the little endian notation. CX. Now I'm applying the Hadamard operator between first, or let's say the top qubit and first qubit. So let's say this is the index of qubits, so 0, 1, 2. So the CX gate on 0, 1 is essentially this from here to here, and similarly another CX operation, or let's say the C0 operation on qubit 1 to 2. This is also called a linear entanglement circuit, and here I have the, okay, let me show you the state vector. So you can see again it's an n cross n matrix, n cross 1 matrix that has a typical shape of 8 cross 1. So it's a column vector or column matrix, and this is an entangled state. This is a linearly entangled state. Thank you very much for watching the demo. Hope you guys enjoyed it. Please like, comment, share, and if you like my content, please subscribe to my channel and have notifications enabled. Thanks for tuning in, and until next time.